am actually here in Hilo, Hawaii, where I live, at the Gemini Observatory North base facility. And we are going to be joining two of their staff members very shortly for our live session. Before we join them in the control room, let me give you just a bit of background about the Gemini Observatory. The International Gemini Observatory consists of twin 8.1 meter optical infrared telescopes located on two of the best observing sites on the planet. Gemini North is located on Hawaii's Maunakea in the summit region at just under 4,267 meters and works as part of the international community of observatories built to take advantage of the superb atmospheric conditions on this long dormant volcano. By incorporating technologies such as laser guide star adaptive optics and multi-object spectroscopy, astronomers in the Gemini Partnership explore the universe in unprecedented depth and detail. Now, just to give you a sense of place, let me give you a live view of the summit region of Mauna Kea. Now, this view is from the Subaru telescope operated by the National Astronomical Observatory of Japan. Here on what would be your left, you have the twin Keck telescopes. Towards the back here, you have the NASA Infrared Telescope Facility, the Canada-France-Hawaii telescope, and right here on the right side is the Gemini North telescope. During the day, you have teams of scientists, engineers, and technicians who are hard at work addressing any issues that may have come up during the previous night's operations. They're changing instruments, calibrating the instruments, and analyzing weather conditions and more. All of these decisions made during the daytime operations help prepare the evening team for a successful night of observations. We have the privilege of shadowing Science Operations Specialist Denise Hung as she begins daytime operations, and they are in the control room right there. And in front of us, you see our guide for this session, Dr. Brian Lameau, staff scientist here at Gemini Observatory North, and he is also one of the co-founders of Shadow the Scientist at the Mauna Kea Observatories. So let's join them live in the control room. Welcome, Brian. Welcome, Denise.
Aloha, Jamaica. Aloha, London. I'm Brian, this is Denise. So we are, as Jamaica mentioned, we're in the Gemini North control room. This is one of two telescopes that the Gemini International Observatory operates. So we're the northern site. We're in the northern hemisphere. We take all the northern sky targets. And then we have a sister telescope, a near twin in Serapichán in Chile. You might be able to see in the background here, it might be a little bit blurry right here. We have a clock for Hawaii, a clock for Chile, and a clock for Tucson. Hey. And those are our three different sites. So Tucson, the organization that manages all of the telescopes as part of our web of telescopes, has some other telescopes in Tucson and could peak. We are just finishing our night here. In fact, all of us who are doing day operations, I do day operations and I also do night operations. I was just on night operations. Now I'm switching over to the day. Sometimes I'm doing 24-hour shifts. Our night crew just finished up about an hour and a half ago because they actually usually stay up until sunrise. We take calibration observations all the way to sunrise. If they're very unlucky, it's even past sunrise sometimes if we have to do integral field unit twilight flats. And then we change out. So we're actually in the transition period right now between nighttime and daytime. In Chile, they're in the kind of mid-afternoon, so they're ramping up to go into the night. We're just checking everything that happened the previous night. So Denise is a science operations specialist. Denise, sorry, I know you're busy at the
Yeah.
moment. You're running the
Um,
Altair Health.
yeah.
So actually, Denise is the one on duty right now. She's actually doing real work. So if you're, are you, can you
Yeah, I
talk
can
about
go
what?
for it
Yeah,
now. So, right now I'm running some instrument calibrations, but basically what my job is during the day is to check that all the instruments work and they're doing what they're supposed to do, and also coordinate work with the summit and anyone else who wants to do some testing with a telescope during the day to make sure we're all operational for the night.
yeah. So we have a 9:30 operations meeting every morning. This is the confluence point for everybody. We have people, we're a queue-based observatory, which means we have people from all over the world applying. We have an open skies policy, so anybody in the world with a good idea can apply to our observatory. We take all of those ideas. Those are ranked dual anonymously in a time allocation committee. About 30% of the ideas get the chance at time on these telescopes. And then they're thrown into a giant matrix, which we call a queue. And we have somebody who's managing the queue. So they look at all the different weather conditions. So right now, right up here, you can see it's a bit cloudy. I can give you a different view, actually. Oh, sharing's not turned on. I'm gonna send a request. But it's cloudy here on Maunakea. We're down at sea level, but up at Maunakea at 4,300 meters, it's cloudy. And so that's not super often that it's cloudy, but we have to make sure that we have observations ready for cloudy conditions. So a Q coordinator on any given day, I just finished a shift doing this. You spend about 8 hours during the day making plans for every possible weather variant. And so that could be absolutely gorgeous skies, which we have a lot of on Mauna Kea. Could be very low turbulence on the ground and in the atmosphere, very low water vapor, no clouds, or it could be fairly, don't worry, that's okay. uh, Fairly cloudy conditions with a lot of turbulence, with a lot of water. And so, as a Q-based observatory, we need to take advantage of every single second that we're open. And so, we have plans for that. And so, this Q coordinator right now is checking all of the observations that we took last night. Denise is also in tandem checking all of these observations. And so, she's checking, we're contractually obligated not to give data that's of worse quality than is requested by the scientists that ask for time on the observatory. So Denise is checking, in addition to making sure all of our instruments are healthy, is checking that every single observation last night was taken within specifications. And if not, then we try to figure out, well, would those data be still usable in some capacity? We speak to the scientists involved and we say, hey, listen, we took these observations. There was a little bit more clouds than was expected, but there was less turbulence. We think the data is still going to be good, or actually it was too cloudy, so we'll retake your data, and then we have a back and forth with them. So this is an active process that happens basically from 8 o'clock in the morning till 9:30 in the morning every morning. It's a very hectic time for everybody. So we thank Denise for allowing us to shadow her here. And actually, so she mentioned the summit. So let me try to share again. Okay, so let me do this desktop.
And can I just say to everyone in the audience, if you were joining us by Zoom, you would be able to put your questions and comments in the chat. But since, of course, you are live there in London, Raja, if you receive any questions, please feel free to convey those to us. Thank you so much. Right.
Yeah, yeah. We very definitely welcome your questions. It's early for me, so I could definitely use some energy. No coffee yet. So this is a different view of Mauna Kea. So Jamaica showed it was the Mintaka cam that you showed, yeah?
Yes.
Yeah. So the Subaru Observatory, this is an observatory I actually use a lot for my research, secretly more than Gemini. Um, so this is on the North Plateau of Mauna Kea, and I was looking back at the East Ridge, actually towards Hilo, where we are. So just over that ridge that you saw is where we are under clouds here. Um, and this is a different view. So this is actually mostly mounted on our dome structure. So this is the Gemini North Observatory here. This is the Canada-France Hawaii telescope. Behind Gemini is the University of Hawaii 2.2 meter, which Denise used a ton for her thesis, tracking solar system bodies. This one here should make you guys proud. This is the United Kingdom Infrared Telescope. It's not owned by you guys anymore. It's the University of Hawaii, but did a lot of good work while you guys were owning it. And so these pictures are live video feeds from the inside of our dome. And so you might even see during this session, we might go back to this, 4 vehicles pull up here. We actually have a day crew that comes every single weekday, more or less, unless the conditions are absolutely crazy. So we do get 130-mile-an-hour winds on the summit. Sorry for the imperial units. We do get ice and snow and fog, so that happens every once in a while. And so as long as it's safe to travel to the summit, people travel there every day. They're actually in a safety meeting right now, so they're probably holding at our midway point called Halipahaku. Because it's 4,300 meters, they have to acclimate. Everybody has to acclimate before going to the summit. So we wait about 45 minutes, kind of minimum, at Halipahaku, which is 3,000 meters roughly. Kind of get our bodies used to the oxygen deprivation. Loosely speaking, it's about 40% less oxygen once you get to the summit. So this is intensive work. Tomorrow, actually, they're moving a several ton instrument off of the bottom of our telescope and putting in another instrument. This is not for the weak of heart. So, I mean, you're dealing with oxygen deprivation. You can't really think that well, and you have to do demanding physical labor. And so they usually get up there actually about this time, but because they're in a safety meeting, they'll probably get up a little bit later. But they'll come into the dome, and once the dome lights turn on and they start moving around the telescope, this is when Denise more or less has to stop her work. And so it's really advantageous for Denise to get in early to take care of everything that she needs to do with the telescope before the summit crew gets up there, because there's only a certain amount of time that we can have people up there. And so we want to make sure, again, that during the daytime, we're using every second because, it's harsh conditions and we want to be able to fully facilitate that work up there. So I'm just going to go, so this is actually a public page. This is another view of Maunakea. This is from the outside of our dome structure. This is looking back Hilo to the east. Not surprisingly, it's cloudy. And then south camera when Kilauea, the most active volcano in the world, is going off, as it just was not too long ago. You can actually see the glow in the south cam. And last time I was on the Keck telescopes, that was December 23rd of this past year. Kilauea went off right while we were taking the observations. We had thin clouds like this, and we actually had backscatter from the clouds we were observing, very blue. And even though lava looks red, it makes a lot of blue light. And so it's backscattering off the clouds. And so the background of the sky was about 10 times what it normally is, just due to the fact that there was these thin clouds and the volcano was going off. So
Yes.
in case you weren't aware, everything is interrelated. We were looking at very distant galaxies that were about 11 billion light years distant. And yet this volcano that was our next door neighbor, just 50 kilometers down the road, was affecting those observations. So yeah, it's amazing. We're still tied to the Earth. Here is looking west. This is the NASA Infrared Telescope Facility, and you can see down here in what we lovingly call Submillimeter Valley is the James Clerk Maxwell Telescope, East Asian Observatory. And then Kona, the other side of the island, is over here. And then the Keck Telescope, and again, the NASA Infrared Telescope Facility. So we actually use this at night. This is a public page, and our scientists who We're a very adept observatory at following up what we call transient phenomena. So these are things that go bump in the night, um, exploding stars, tidal disruption events for stars getting too close, dangerously close to a very massive body like a black hole, a variety of other phenomena. And so we have latent programs in our queue that can be triggered basically at any time. And the scientist sits in their bedroom, basically, or in their office, or whatever time of day it is. They get an alert from a smaller telescope, or usually a system of telescopes, that are kind of scanning the sky. The Rubin Observatory is one of them. So this is a new observatory that is also operated by NORAD Lab, which Gemini is under. This is also Serapachon, and this is an 8.2 meter telescope, 8.4 or 8.2. And it's scanning the night sky every 2.5 nights. Yeah. So basically what they look for is differences between the previous scan and this scan, and they find a lot of them. And some of those are garbage, but after they do all their filterings and filter out false positives, there are genuine events left. And then one has to ask the question, are those asteroids that are just wandering around the solar system? Are they comets? Are they hot pixels or something we did wrong in our calibrations? Oh no, that's definitely a galaxy. That galaxy is definitely brighter now than it was before, and it's just a small part of it. And these events, they have as much luminosity as the entire galaxy itself. So a supernova can be more luminous than its host galaxy. And so in theory, these things can be relatively easy to spot, but in practice, very difficult. It's a big sky. And so they get this alert, they click a button, and we're hoping in the future they won't even have to click that button, and the alert will just pipe directly to our system. But for now, they click a button, they wake up, and then they press a button, and then we wake up, and then we actually have a sound that comes here that says "Attention, target of opportunity." If we're during the day, the Q coordinator will scramble to remake the plans, especially if it's we class a rapid target of opportunity. If it's a nighttime, the observer immediately looks at the program, understands, okay, this needs to be taken right now, or it can wait 30 minutes, or it can wait 2 hours, or whatever. Sometimes they call the person who pressed the button and said, okay, just to clarify, you want us to take this right now, right? Yeah. Okay. And we slew the telescope, and we go over and take that observation. And so those scientists can actually look at this page, and you see up here, it says TOO availability, that's target of opportunity availability. They can look on this page, they can see the weather conditions. We have all this information on the right-hand side here, which is very specific quantitative information about the weather. And they can say, I don't like those weather conditions. Maybe I want to go to the south. And so then they might have a program in the south, and they say, what time of day is it in Chile? Oh, dang it, it's daytime. Okay, too bad. But if it were nighttime there, because we're 7 hours or 6 hours right now difference, they could say, maybe it's better to trigger in the south, and the weather looks better there, so I'm gonna trigger there. And that's one of the wonderful things. We're offset in time. We're at +20 latitude, they're at -20 latitude, so they can cover parts of the sky that we can't. We can cover parts of the sky that they can't, and then there's a huge overlap region. And so if it's what we call an equatorial target, so it's on the celestial equator, so basically just the projection of our equator out into the sky, then either observatory can look at it. And so a scientist might decide based on the weather, based on the time of day, yeah, it's better here than elsewhere. So we actually had this last night. Oh, yeah. So Denise, can you bring up it was ED 102? Actually, I'll have to modify it in the second one. So, yeah, sure. Oh, no. And then 109. Why are they doing that? Back maybe like six back to the act.
Brian, I'm going to fill in a little bit while you're doing that.
Please.
So Brian forgot to mention that he was a UC Santa Cruz undergraduate.
Fair enough.
Yeah, go banana slugs. There's
banana slugs.
And I had the privilege of being his senior thesis advisor. And it's such a small world because the transients he was talking about, one of the leading facilities for that is in Chile. The Rubin Observatory is going to produce 1 million of these alerts a night. And the person who was the brainchild for that was one of Brian's former colleagues at UC Davis, Tony Tyson, who happened to be my PhD thesis advisor. So it's all very connected and interconnected in multiple ways. Just wanted to interject that while you were looking for the target. There you go. Back
Thank
to
you
you.
for the thank you for the context. And in fact, Raja, the first time I was ever observing on Maunakea was with you back in 2003. So it's been 23 years since I first, more than half my life, well over more than half my life, that I have been coming to the Big Island to observe on the facilities. I won't tell you which observatory it was. But yeah, so we're all a wonderful community here.
We
Yeah.
are. That's right. That's right.
Healthy competition. Okay, so I'm gonna go. Yeah, so this is actually last night's data. Okay, so this is the acquisition observation. So we have Gemini is very lithe. It's one of the fastest telescopes in the world, big telescopes in the world. We switch instruments, so we have multiple instruments on in a given night. We switch instruments faster than any other 8-meter class telescope. We actually can switch instruments in about 20 seconds.
Impressive.
So we have, so just for like context, Keck, if they're doing 2 instruments in a night, it's about 10, 15 minutes switch. Subaru can be up to half an hour, depending on the 2 instruments. CFHT takes a whole day, Canada France Hawaii telescope, because they actually have to physically remount another instrument onto their, well, it depends if it's prime focus or onto their CAS port. We have a bunch of instruments sitting down at Cassegrain focus, which is the bottom of the telescope, and we have a tertiary mirror that flips between the different instruments. And so this is an optical image. So this would be basically how humans would see it. It's in the R band, so it's red-ish for us. But this is a false color scheme, so this is just more or less black and white. And so this is an acquisition observation. And so this is a galaxy here. This is one of many observations that we took last night. So it was actually quite cloudy, so the observer was bouncing in between our like kind of poor weather observations, which are really bright targets. And then it was pretty cool to read the night log. She was like, found a hole in the clouds, going for the gamma ray burst. And it's fun. It's like at nighttime, it's it's a lot of action.
It is.
It keeps you awake for sure.
Definitely.
On those long winter nights, it's helpful. But yeah, so target of opportunity came. It was let's go turn to the observation as soon as possible. She found a hole in the clouds, went after it. This is an image of the galaxy, the host galaxy. This thing right here is the optical afterglow of a gamma ray burst. And gamma ray burst is a very high energy event that usually comes from a very massive star collapsing or some phenomenon similar to that. And so as you can see, this source here, it's not tough to spot. I mean, if you didn't know what you were looking for, okay, but because there's a lot of little blobs there, but you can see the disk of the galaxy here, and then you just see this random bright clump sitting over on the side. And so this shadow, actually, maybe it can't come through, but this shadow right here is the shadow of the slit that we put on for slit spectroscopy. And so then we take an image of the slit. We then should be the image. Oh, it crashed.
Brian, do you have a before and after image of the supernova of the gamma ray burst? Do you have a before image as well?
We don't actually, Raja, but I'm sure somebody does.
Okay. So what I mean by before and after, this is how these triggers are generated. You take digital images, a patch of sky, and you take a difference between your current image and an image that was taken before. And that difference tells you what's changed. If something has moved, something has brightened, something has gotten darker. So that's how the Rubin Observatory generates these alerts. It takes images of certain patches of sky that it has imaged before, and those reference images are subtracted from the image of the night, the current image to look for differences. It's called difference image analysis, and it's a very simple technique. It's a great way to look for motion or change.
Right. So those are just images, and images are great, but what you really want is spectroscopic information. And this is actually what I did my senior thesis with Raja on, was using a large slit spectrograph to take observations of distant galaxies. This one is a fairly close by galaxy, local neighborhood, 1 billion light years. Cosmologically close. But thanks to Raja, I can actually recognize these lines by eye. Raja, you know what those are? Yeah. Keep in mind the blue axis so blue is to the right.
H beta and O3.
Exactly. Yeah.
H
So this
beta
is
on
like
the far right and O3, yeah. 4959 and 5007.
exactly. Yeah. So this is I mean, every spectroscopist knows this set of lines. So this is hydrogen emission, and then doubly ionized oxygen emission. And so these are actually really broad lines. I could maybe do a cut really quick. So this is an in-house software, by the way. This is like science operations specialists like Denise write this kind of software for us. So this is what's called a one-dimensional spectrum. It's a 2D graph, but so this is wavelength basically on this axis, so color, and then the intensity of the line. And so the ratio of this line to this line, the intensity can tell you all sorts of wonderful things about the properties of the gas that's surrounding the supernova. The width of the lines can tell you something about the velocity. You can work out the hardness of the radiation spectrum. So how many high energy photons are there relative to low energy photons. And so astronomers can piece this all together to get a physical picture of what this phenomenon was that created it. The before image also helps in that case, because you can isolate which potentially, if it's high resolution, which source was the one that actually gave rise to this event. And then they can understand, okay, yes, this thing is expanding out at thousands of kilometers per second. It has tons of high energy photons. Then they go back to models and say, okay, that would be this type of source. Is that consistent with all the data? Yes, no, so on and so forth. And then rinse, repeat. Okay. And then they say, oh, no, it's ambiguous still. We need to target another one. And so this one actually came through a director's discretionary conduit. So it was so exciting that somebody said, hey, director of Gemini Observatory, could you please give me like an hour or two every couple of nights to follow up this target? And the director in this case said, yep, absolutely, sounds good. And so this is why we're taking these observations.
Incredible, Brian. With just about a minute and a half left before we transition to Q&A and you all get ready for your science meeting.
For a minute.
What is the plan for this evening after Denise and all the rest of the engineers and technicians do the daytime operations?
So actually, I am in charge of one of the instruments. It wasn't super happy at the end of yesterday, so I'll probably work with Denise to try to figure out what's going on with that instrument. It's either a mechanical issue or software issue or some combination of the two.
Is this GNairs?
GNairs, yeah. Mm-hmm. So we're gonna baby it on calibration. So I'm gonna work with Denise to do some calibrations and see what's going on with the instrument. Then we actually feed that information over to our Q coordinator, because if the instrument's not healthy, then they have to make a plan without that instrument, right? So, and we don't want them getting a call at 2 a.m. saying, hey, the instrument's broken, can you remake the plan from scratch, which has happened. Has happened. And that's not a fun call to get at 2 a.m. So the Q coordinator will start making plans again. They'll assess the data quality of everything that we took last night. And then throw everything back in a matrix. It's our last night of our IGRINS 2 instrument, which is a extreme radial velocity near infrared spectrograph, which basically means a planet finder and a stellar atmosphere characterizer. And so this is our last night before we switch out for Maroon X, which is another extreme precision radial velocity, but in the optical spectrograph. And so we're going to try to do as much IGRINS 2 tonight as possible. I think we have a planetary transit tonight, so that's the exciting thing.